today's session. Okay. Uh, Hello again. I hope you all had a good time so far. Now, today we are going to talk about the Class B and Class AB amplifier and how we can design the Class B, which is basically the base of Class AB. There is a very little difference between the two, which we are going to talk about. Now, the Class AB amplifier, as we talked before, involved as basically contain two switches, one NPN, another one is PNP. Okay, so when you want to uh, implement the circuit, you need to make sure that first of all you use one NPN, one PNP, and since the direction of the current between the NPN and PNP are different, and we all know that the current goes from the higher potential to the lower potential, you need to make sure that you connect the terminals, the emitter, collector, and base properly. You're not going to make a mistake over the base, but the collector and emitter could be a source of a common mistakes or basic mistakes, and your system would not work properly. So we have collector, emitter, and base in a first switch, and again, emitter, base, and collector in the second switch. Now, in the simulation in the exercise, the circuit that I provided for you did not have any biasing circuit. Okay, so you simply drawing or simulating the simplest design, okay, which is like a conceptual, design of a Class B amplifier. But we all know if we want to have a proper performance, when we talk about the transistors and BJTs and MOSFET, we need to have a proper biasing and a strong proper bias, okay, to make sure that we do not leave, like for BJT, the active mode and get to that saturation mode where we don't have any control over the gain. Are we good so far? Now, how we do that? Here, we have a voltage division circuit, which we are using for the biasing. It includes three resistors, R1, R2, and R3. R2 is the resistor that connects the two bases to each other. Okay, so it's between the base 1 and base 2. And R1 and R3 connecting respectively the base 1 to the VCC and base 2 to the ground. Are we good so far? Now, we wanted to design this circuit. When we say design, the main goal is to first, we know how much collector current we want, okay? Since they are in series, both of the collector current are equal to each other. And we want to have a strong biasing for our BJT. Before we talked about the strong biasing, we said, okay, when we have an IV characteristics for the BJTs, okay, in order to make sure that we never leave the active region, what we have to do is to put the Q points in the middle of the line, the Q line that we had. You remember we had the IV characteristic, okay, and the IC, and we had a Q line which defines basically the characteristic of the load based on the voltage that we have over VCC. You remember that? We talked about that. Now, in order to have a strong biasing point, these are more. We want to be in the middle of this line. So if we have positive or negative variation, we make sure we are in the best spot to avoid exiting the active region. Are we good? Is that clear? Why we using that? And again, we already talked about that. If we wanted to be in the middle point of our line, that means the VCE should be half of the total volt. That was for one BJT. Do you remember that? So we will set, like for example, if we had the VCC and one BJT, so we had a VCC and one BJT, emitter collector base, we want, and this was 12 volt, we wanted to this voltage VCE become 6 volt. Now we design the rest of it to gain that volt based on the collector current that we have. Very good. Now we have two. I don't have a razor. Okay. Now we have two switch, and again we want to make sure that we are in the middle of the Q points for ROS. What that means? That means if we draw the line to cut in half the circuit, okay, half the voltage, half the VCC voltage should happen above this line, the middle line, and half of it should be below it. So, for example, here we have VCC equal to 12. Okay, so this half should be 6 volt, this half should be, again, 6. Are we good? So this is how, this is like a rule of thumb, okay? So we have to design our biasing circuit in a way that we make sure we have those voltages around what we aim for. Are we good? Now, if we have a strong bias, that means the base emitter voltage here should be around 0.7. You remember that? So this is 0.7. Same goes, this is for first switch, this is for second switch. Same goes for this one. Again, this should be 0.7. Are we good? What that means? The first conclusion that you can get is the voltage between the two base is going to be 1.4, around 1.4. Are we good? It's simple KVL. Okay? So the first result of this assumption, which is the result of a strong bias, which we want to have, okay, is that the voltage between the two bases are going to be 0.7. It is not equal, let's say around, we are going to talk about that, plus 0.7, which is 1.4 volt. Again, let's put around that area. Okay? Now, what is the voltage between the base 1 and base 2? This is the voltage across R2. Are you good? So keep that in mind, that the voltage across R2 is the same as the voltage between the two bases. Now, how we could determine the values of R1, R2, and R3 to make sure we have the characteristics that we want. Okay, the most important one is the I of the collector, the current of the collector. And we have a strong bias, which we define it as half voltage above and half voltage below that line. Okay, now, if the collector current is 100 milliamp, this is my assumption, and my beta for both of the BJTs are 100, that means the base currents are going to be both of them because we have both of them equal. We consider both of them equal. Okay, so you have to make sure you're considering the specification of your own model when you talk about the designing the circuit. Okay, the current of the beta, the base is going to be the collector current over beta, which is 100 milliamp over 100, which is 1 milliamp. So in order to have collector current of 100 milliamp, I need to have 1 milliamp injected to the bases each. Okay, so 1 milliamp here, 1 milliamp here. Is that good? So far. Now, when we talked about the strong biasing, and we know we supply the power of our system by VCC, which is a DC source, and our signal is going to be an AC. Okay, so what that means? That means whatever voltage we have here, which is the voltage of the bases, would experience a certain transient with an offset of the DC. Are we good? What that means? That means you already know that we have an internal resistance here, or the lowercase re that we talked about before, here and here. That means if we have a variation of the voltage here, our base current also would follow that variation. Okay? We don't want that. Same as if this is if the I of base varies, that means the collector current also varies. So we miss our goal. In order to do that, we want to make sure that there is no effect of, or we want to minimize as much as we can the effect of the VCC here. So whatever this one sees is only the AC signal. Are we good? How we can do that? We have to make sure when we designing the biasing circuit, the current that is drained from the base, the DC current drained from the base, is very low, close to zero, or you can say negligible compared to the voltage, to the current that's passing through the voltage divider. Are we good on that? Is that clear, the condition? Okay, so how we can do that? By simply design the voltage divider in a way that the current going through here, let's say I1, okay, is going to be much larger than the base current. So we want I1 to be much larger than the base currents. Now, normally, there is a scaling factor that you can choose in order to make sure that your currents meet this condition. Okay? I'm too conservative, so I'm going to choose the scale factor, let's say alpha of 20. So I want to design my voltage divider, so I make sure that the current one is 20 times of the current base. So when we talk about the current division, the base current is basically negligible compared to the current that going pass through the voltage divider. Is that clear? Now, if the base current for our goal, 100 milliamp collector current, is 1 milliamp, and we chose the scaling factor of 20, that means we have to design the voltage divider. So the I passing through the divider, I1, should be 20 times that, so it should be 20 milliamp. Are we good so far? Now, the current passing through R1, since this is too low comparing to that, we can say, okay, this current passing here without any changes to R2 and to R3. So these three resistors share the same current. This is approximation. This is not exactly, because you know there is going to be a base current. We can't eliminate that in reality. What we can do is to lower it as much as we can. Now, you remember the voltage across R2? It was the voltage between the two bases, which was around 1.4 volt. So now we have the voltage across R2 and the current passing through R2. Simple Ohm. R2 is going to be the voltage across R2 over the current passing through that, which is 1.44 at 20 milliamp, which is, if you do the calculation, is going to be 70. So far, one of our resistor, we find the value that we need for the strong biasing in our circuit. Now, how about R1 and R3? Now, this is a voltage divider. Okay? The voltage between these 2 points, the two bases, are of 1.4, and the whole voltage from VCC to the ground, what we have is 12. That means the voltage of R1 across R1 plus the voltage across R3 should be 12 minus that 1.4. Again, a simple KVL. If you do the math, 12 minus that is going to be 10.6 volts. Are we good? Now, what was the assumption that we made? So we make sure we are in the middle of that load line. So our Q point is the middle of that. What was the assumption that we made? Half voltage up, half voltage down. Are we good? That means both of these voltages should be equal to each other if we want to guarantee that condition. Which means the voltage R1 is equal to the voltage R3, which is half of this total voltage, 5.3 volts. Now you have the voltage across R2 and R1 and R3, and we already know the current. Again, Ohm law. And this is a very simple kind of like Ohm law, again, concept that since the voltages are going to be equal to each other, R1 and R3, and the current is sharing between them, are equal, so R1 and R3 should be equal to each other. So R1 is equal to the R3, which is equal to the voltage across them, 5.3, over the current passing through them, that 20 milliamp. Can you see that? I'm going to move it. Yeah. Which is 2.65. Right? Am I right? 2.65, but there is a 10 here, so 0.65 kilo or 265 ohm. Did I get right? The calculation is right. 2.65 and one shift because of this 10.
Yeah, you did it.
And yeah, okay, right. So we know everything about our Class A amplifier. and we design what we want based on what the goal is. Now, your beta is different. Maybe your collector current is different, or your source voltage is different. Okay? So you might have a different numbers for R1, R2, and R3 based on your specification, but you know how to solve. Also, this alpha is your choice. So I chose 20, you can choose 10, but don't go lower than 5 because then it's not a scaling factor anymore. A proper scaling factor. Are we good? Now, we already talked about the problem that the class B amplifier. And we said the crossing point when the AC signal here crosses the zero. Okay, so we have a signal in our input in the region that it crosses the zero. Okay, we have a problem with the two switches. Why we have a problem? Why there is a problem in zero crossing? Go ahead. It is basically the voltage of base emitter is below what we want to what we need to turn on the switches. Okay, so let's say this is the line. Let me choose another color. Let's say this is the line of threshold. Now we have two NP, NP, NP. One of them works in a positive, another one works in a negative. So we have two lines of a threshold. Below or like between the two lines, none of the switches are on. So what we are going to see at the output, is that we are having zero, and then when we cross this threshold, now the first Q is conducting. Then again, we are going to have a little bit of zero when we are between the lines. And then the bottom Q, the Q2 is conducting. And again, we are going to have zero and repeating. So we have a distortion when the signal crosses zero. And the reason was because this base emitter voltage between the two threshold line is lower than what we need, so that both switches are off. Are we good? Now, class AB would fix that by making sure that we always have the voltage we need to turn on the switches. How we do that? We simply replace the R2. We replace the R2, so we get rid of this. We replace the R2 with a 2 diode. Pay attention to the direction of the diode. So the a higher voltage should be the voltage related to the Q1. The lower one should be the one related to the Q2. Are you good? Now that we have two diodes, we already know that when those diodes is conducting, which is basically all the time because we have a VCC here and the ground here. So this is eliminated. So the current goes through here. So these two diodes always are conducting. Are we good? Anyone have problem with that condition or assumption? No? So if we have the two diodes conducting, we talked about the constant voltage drop model, which means when the diode is conducting, we can replace them with a constant voltage. What was that constant voltage? 0.7. So we have two 0.7 constant voltage between the two bases. So we are going to never be short of voltage on the both base emitter voltage. This is true. In reality, that's not going to happen. Why not? Because we consider this as 0.7 volt. Okay, this is the source, okay? So don't consider that as P, please, here. We are not going to have exactly 0.7. We said it's going to be near 0.7. So it might be 0.6. Okay? Same goes for these two. These are near 0.7. So maybe it's 0.65. And this one is 0.6. So there are some conditions that we don't meet the voltage base emitter threshold. Is that clear what we're talking about? So theoretically, this would eliminate this distortion. In reality, this just decreasing that distortion. So if you see in your oscilloscope that you still have distortion, that's very kind of like okay, and it's very normal. And it's because of the reality versus theoretical voltage across the diodes and the real threshold voltage that base emitter for both of the switches. Class B amplifier doesn't have any specific design. The only thing that's happening is that you replace the R2 with those two diodes. So whatever you did here is going to be the same for the design of the class A B amplifier. The only thing is that you don't need this VR2 because you have two diodes that will always conduct. But the rest is the same. Are we good? Any questions?
For the capacitors, state
in your case, is not. It doesn't matter. But if you want to like know how to design it, it depends on the frequency of the signal that you want to like inject. Okay, what this capacitor basically do is like acting like a low pass filter. Okay, so run a KVL, run a Thevenin theorem from this terminal, okay, and you are gonna have a resistor and a voltage source for the whole amplifier. Okay, now you have a RC circuit. Okay, is that clear? You have a RC circuit that for the DC source, for the Thevenin voltage, this is open circuit, so you can ignore that. For the AC one, it's conduct. So you have an AC source, you have your capacitor, and you have your Thevenin resistor. Now, you have like a 10 hertz signal or 1 kilohertz signal. You can design this, the cutoff frequency, which is 1 over 2 pi RC, at a value that you make sure that you do not attenuate your input. So, meaning if you have like a 10 hertz, so you have a very low frequency in your signal, your cutoff frequency should be way back, very close to the zero. It creates some problem because now you don't have a proper attenuation for the DC. Okay, when you have a low frequency signal. But you need to have a untouched AC signal when it comes to the circuit. If you have like a 1 kilohertz kind of like signal, which is normally is around that. Normally your input signal is high frequency. Okay, so if you have a high frequency signal, then you have a freedom to choose that cutoff frequency like in 100 hertz, somewhere around 100 hertz. Now you make sure that your DC is taken care of. Oh, sorry, is a high pass frequency. I'm sorry, is a high pass frequency. You can make sure that your DC component is get rid of, and your high frequencies pass through without attenuation. Are we good? Any other? Did I answer the question? Any other question? Yeah, good.
Could you just explain the and reduce the distortion?
Okay. When you had a diode and you connect them, basically you are connecting when you connect the anode of the two diode toward the VCC and the cathodes toward the ground. That means they are always in forward bias. Are we good for that? Because we are connecting the higher voltage to the lower voltage. This is the circuit, correct? So these are both in a forward bias. We talked about the constant drop model voltage, constant drop model, when we talked about the diode. And we said if we have a forward bias diode, we simply can replace it with a single constant voltage drop, which we said for the diodes, like silicon-based diode is 0.7. For the germanium was 0.3.
So when we add those two, since now those don't have any consistency, just get voltage drop and we recalculate what R1 and R3, we still get the same.
You're gonna still get the same because before, first of all, did I answer your question? Yeah. So before, when we didn't have these diodes, we designed it for ideal case, which these two are 0.7. So still we had 1.4 here. Now with the diode, we make sure that we always have 1.4 here. Okay, so for the rest of the circuit is going to be the same. The only thing that you change is that you don't need the R2, so forget about that.
Becomes R1 plus R3, 10.6, and then you just go.
Yes, you start from here. Okay, so the rest is except this one because you need to have a current. The R2 and VR2 is not necessarily, you don't have it.
Base minimum that has to be 0.7 or it's sure only flows when they're not based 0.7 volts. There's always enough current for both transistors to be conducting, so it minimizes.
There are always not the current. There are always enough voltage between the base and emitter, so we make sure we are in an active region. We have a proper biasing. Our switches are altered.
Not.
Yeah. Any other question? Are we good? Okay, if there is no question, that is for today. I just wanted to point out how you can simply design the class B and very easily change it to the class AB. So when you are going over the last exercise and the second to last exercise, I think you know what to do. Good? Thank you very much.